Okay, welcome to lecture number 48. In lecture 48, we have first typical property of congruent circumradian. It goes like this. Suppose we have two segments, AB is congruent to PQ, and we have 2 points X and Y such that whatever this angle X is there by this point X, and suppose we have the same angle, they are not congruent triangles but the angles are same. So if we have same angles at two different triangles, this is congruent, then what can we say about circumradius of triangle XPB, circumradius of triangle XAB and YPB PQ. What can we say about it? That is a good question. You can think about it and answer. Given AB congruent PQ and angle over here is same. In that case, the answer is circumradii of both these are equal. Now, why are they equal? They are equal because we can prove it in two different ways. Number one, we can put this triangle on this, and therefore what will happen is A will coincide P, B will coincide Q, and this point Y, and this angle will be X. So XYBA will be cyclic quadrilateral because of inscribed angle property, and therefore they will have, both of these triangles will have the same circle, and therefore circumradius will be equal. That is one way of proving it. Second way of proving it is inscribed angle is X, therefore central angle of this triangle, if we draw circumcircle of this triangle, then central angle will be 2x, and central angle in this case also will be 2x, and because angle is same and the opposite side is also equal and it is isosceles triangle, therefore both the triangles, both these red triangles are going to be congruent, and therefore circumradius of triangle XAB will be circumradius of triangle YPQ. Another question in the same context is, suppose we have segment AB and suppose we have angle X here, and we have congruent segment PQ, these two are congruent, and then the angle is not same but it is supplementary. This is X, this is Y, and it is given X plus Y is equal to 180. In that case, what is the relationship of circumradius of XAB with that of YPQ? Again, this is another interesting question. You can try this, but the solution goes like this. Now you copy this angle and paste it opposite way, upside down. Okay, so if you paste it upside down, you will get this angle Y, and X plus Y is given to be equal to 180. Therefore both these triangles will have same circumradius. So that is first part of the lecture number 48. Second is, there is a theorem which says circumcircle of triangle ABC, angle bisector of angle A and perpendicular bisector of segment BC, they are concurrent. So the theorem goes like this. You have a circumcircle of triangle ABC, you have triangle ABC, and then if you draw angle bisector of angle A, it intersects at L. Suppose angle bisector, internal angle bisector of A intersects circumcircle at L, then we have to prove that point L, and let us do it simultaneously, that exterior angle of A intersects the circle at L dash. So this is Y is equal to Y. Exterior angle, bisector of angle A, it intersects circumcircle at L dash. Then to prove that L and L dash lie on perpendicular bisector of BC. So this is what is this theorem. So this point L is a point of concurrency of circumcircle, internal angle bisector, and we are supposed to prove that it is perpendicular bisector of BC, and if we extend this line, of course this is going to be circumcenter. So this is a good problem to prove independently, but if not, you can watch the video. Now if we join these points L and L dash with B and C, then what we will get here, if we show that point L is equidistant from B and C, we can show that L is unperpendicular bisector. Similarly, if we show that point L dash is also unperpendicular bisector, that means L dash B and L dash C are equidistant. So how do we show that L is equidistant from B and C? Now here, if we consider this segment BL, consider BL, segment BL, it inscribes X angle in this circle, X, and segment CL also inscribes X angle at A. So two segments are inscribing same angle in the same circle. That means their central angles are same. Central angle of BL is going to be 2x, and central angle of LC is also going to be 2x, which is 2 times this x and this x. Okay, and now we have done the theorem that if two chords in a circle subtend same angle at center, then they are congruent. Therefore we get BL congruent CL, BL congruent CL, and this implies L is on perpendicular bisector of BC. Similarly, we can prove that BL dash and CL dash also lie on perpendicular bisector. Here we need not have to do anything. We know that x plus y is 90, L is on perpendicular bisector and on circle, and therefore LL dash must be a diameter, because any angle inscribed in semicircle is 90, the other end must pass through diametrically opposite point. Therefore L dash lies on diametrically opposite point on the circle of L, and hence exterior angle bisector also passes through L dash. So this is what is our theorem number 2. Now there is an activity which is finding out length of angle bisector in the lecture number 48, but otherwise the content of lecture 48 is little big for a video. So what I will do is, lecture 49 is little small, so I can take this finding out length of angle bisector in lecture number 49 and finish the remaining part of lecture 48. Here another important formula we can derive is area of triangle. One more formula for area of triangle, because now we have done similarity. So if in a circle we have a triangle ABC, we have this diametrically opposite point A star, ABC, this is diametrically opposite A star, therefore this is O, and then we have altitude D. Okay, now you must notice that A and A star are diametrically opposite, therefore angle at C is 90 degree, and if this angle is capital B, then this angle also will be capital B, because AC inscribes angle B at B and AC inscribes angle B at A star. This gives us the relation that triangle ABD is similar to triangle A star C. Correct? If we write ratios, we get AB upon A star is equal to AD upon AC. Now, AB in our other notation is small c, A star is diameter, therefore it is 2r, AD is height of triangle, and AC is small b. This implies H is equal to BC upon 2r. Okay, and now if we want to find out area of triangle ABC, which is delta, which is half small a into H, which is ABC upon 2 into 2r, which is 4r. So this is yet another formula for finding out area of triangle, having known all the three sides of the triangle and circumradius. This is very useful. So maybe this is ninth formula of finding out area of triangle. Okay. Now the last thing that we need to do in lecture number 48 is what is called power of point. We have already seen what do we mean by PA into PB is equal to PC into PD. So this is extension of that. In a circle, if you have two intersecting chords, something like this, A, B, C, D, and this is P, and the moment you draw circle, you have a center fixed, radius is fixed, and the moment you take point P in the circle and pass whatever number of chords through P, we have PAPB into P is equal to PCPD. That is what we have seen. PAPB is equal to PC into PD. Now, if we draw a special chord passing through center, suppose center is M, and then this is E and F, then this is also equal to PE into PF, right? Now, this quantity normally is called power of point, PAPB, PCPD, all these three are equal and it is called power of point. Now, if we take the last ratio, PE, I can convert PE into PE is PM plus ME, which is R, capital R, circumradius of the circle. And the PF, if I want to write, it is maybe R minus PM. Okay, so R plus PM and R minus PM makes it R square minus PM square. So this is constant. The moment you have a circle in place, its center and radius is fixed, so capital R is fixed, and the moment you have point P in the interior of circle, PM is also fixed. So power of point is R square minus PM square in this case, and that is what is given in this lecture. Then there is a practice problem set which involves 4 camouflage problems and some computations of areas and lengths in a square. So that is what is lecture number 48. As I said, length of angle bisector we will find out in lecture number 49. Otherwise, that's all for now in lecture number 48. See you in lecture 49. Thank you.